Welcome to Curie Electronics. In this video, we are going to learn about LVDT or linear variable differential transformer. What is this LVDT? LVDT, linear variable differential transformer. It is a sensor. To measure the displacement, we use this LVDT to measure the displacement, or we can call it as a transducer also. Transducer. I hope you know what is a transducer, or else you can watch the video on the which shows on the I button. Now, this LVDT we use it to measure the displacement. So it converts, this LVDT converts linear motion or linear movement into electrical signal. And it works on the principle of Faraday's laws of electromagnetic induction. So based on what principle it works? It is the Faraday's law of electromagnetic induction. Law of electromagnetic induction. Electromagnetic induction, which we use in transformer and motors and all. Okay, so it's a sensor. It converts linear motion into electrical signals, and this LVDT works on the principle of Faraday's law of electromagnetic induction. Before going to how this works, I will tell you how can we connect two inductors. Assume we have two inductors, that is L1 and L2. These inductors or the coils of a transformer, it will have a dot end and undot end. Where the current end, where the winding starts, that is the dot end. So for this is the dot end. And this coil also, this is the dot end. If we connect these two inductors or coil like this is known as the aiding mode or aiding connection. So whatever the voltage developed across L1 and L2 get added. We can connect these inductors in one more way, that is the opposing mode. That is, we have two inductors L1 and L2. We connect this undot ends together, and we take this if we connect the two inductors or coil like this is known as the opposing mode. Opposing. Now what happens in the opposing mode? Whatever the voltage induced across L1 and L2 oppose each other. That is, they cancel each other. So now let's see what is the working principle of this LVDT. We should have this LVDT is similar to a transformer, okay? It is similar to a transformer. We should have a core. So this is core. So similar to a transformer means you should have a primary winding as well as the secondary winding. So this is the primary winding, and we are going to excite with a AC supply, or not our home AC. It will be a little more higher frequency, up to 10 kilohertz it can go. And this is the E in, input voltage to the primary coil. And secondary will have two coils. There are going to be same number of turns and all, okay? So only I am drawing it. Now, here also we will make the dot end and dot end. So this is the dot end of the transformer. This is also the dot end of the transformer. This is also the dot end of the transformer. Now, for an LVDT, the secondary coils are connected in opposing mode. So how do you make the connections? These two, that is the undot ends, we will connect together and we will take the output across the two dot ends. So this now it is connected in opposing mode, and the voltage developed across the top coil, we can call it as E1, and the voltage developed across or induced across the top coil, the below coil, the bottom or downward coil is E2. Now what is E out? E out equals E1 minus E2. Now when the core is positioned in a particular position, the E out is going to be 0 voltage, and that position of the core with respect to the coils is known as the reference point or null position. Let us take this as the reference point or null position. A reference or null position. Now, if the core moves up or down with respect to that reference point, we are going to get output voltage. Now, what happens if the core moves upwards? See, if the core moves upward, what happens? If the core moves upward, now before going there, I like to show a waveform for this primary and secondary coils. So we have two primary coils and two secondary coils, one primary coil. So here, see, this is the input waveform, that is what E in. Next is E1. See, E1 is going to be in phase with the E1. This is E1, but E2 is 180 degree out of phase with the E1 or input E2. Now this E1 and E2 cancels each other. That is why when the core is at null position, we are going to get 0 volt output. Now let's see what happens when the core moves upward. When the core moves upward, I'll write it as case 1. What happens? Upward. The core is moving upward. When the core moves upward, what is E out? E out equal to E1 minus E2. So when the core moves upwards, the voltage E2 is going to be reduced because less magnetic flux. So we will get a positive value. From this positive voltage value, we can identify what is the displacement of the core as well as the direction of the core. Now, one more case is there, that is downward movement. What happens if the core moves downward? That is a case 2. Let's take it as a case 2. Now, the core moves downward. When the core moves downward, E out, what is E out? E1 minus E2. What it is going to be? Now, E2 is greater than E1. So, we'll get a negative voltage. From here also, we can identify what distance this core has moved as well as the direction of the movement. So this is the working principle of LVDT. The movement of core with respect to the coil produces output voltage that gives the distance as well as the direction of the movement. It's very simple. Let's see quickly what are the advantages and disadvantages of this LVDT. Advantages. Okay, I forgot to tell you this LVDT used to measure the distance, and it is from 2 mm to 250 mm. Advantages. Linearity. Up to 5 mm it is highly linear. Okay. And this, what about the resolution? Infinite resolution. Why we get infinite resolution? Because it is a analog sensor and it gives continuous output. So it is known as infinite resolution, and it has got high sensitivity. High sensitivity means it will give more voltage for a very small displacement. That is, it gives 40 volt for 1 mm displacement. And something called ruggedness. I know you know it is what is ruggedness. Ruggedness means it is very sturdy, solid. Due to that, this is used in aerospace applications and military applications. Then another advantage is the low hysteresis property of the LVDT. Due to low hysteresis, the repeatability is good. Repeatability is good means what? See, for 1 mm movement, this LVDT give 40 volt. If you do the same experiment 1000 times also, or 1 lakh times, you are going to get the same reading. 1 mm movement, 40 volt. That is due to the low hysteresis property. And it consumes very less power, less than 1 watt. These are the advantages of LVDT. Then, what are the disadvantages of LVDT? This is a magnetically coupling sensor. So, stray magnetic field can get induced in it. So, to avoid stray magnetic field, we have to provide shielding for this LVDT. We have to provide shielding. Then one more thing is that what is the output? Output is AC. For the processing of this output, our modern day microprocessor, microcontroller, PLC, they need DC. So what we do? Using a demodulator, phase demodulator, and a rectifier filter, we will convert it to DC. This DC can be used, or we can convert that DC to AC, that is 4 milliamps to 20 milliamps. So more suitable for PLC applications. So that is it. So it is AC, but modern day processing need DC. And the performance of LVDT depends on temperature and vibration. If there is temperature variation, this value, the display, the whatever the voltage provided by this LVDT is going to change, as well as if there is a vibration, it won't be able to give a stable value. So these are the disadvantages. So it's a simple topic but interesting, and it's a sensor. I hope you understood the basic of LVDT, linear variable differential transformer. So if you like the video, please share with your friends. Don't forget to hit the like button. Thanks.